Welcome to my presentation today. My name is Colin Birkenbihl and I'm working at the Fraunhofer Sky Institute in Bonn, Germany. My talk is titled Synthesizing Realistic Patient-Level Data Using Multimodal Neural Ordinary Differential Equations. As most of you are aware, patient-level data build the basis for many research projects in the biomedical domain. This could be basic research, such as discovering new biomarkers or modeling disease progression, but they also find a lot of use in clinical trials where we compare treatment and control groups to evaluate the efficacy and safeness of drugs. Working with patient-level data, however, is always accompanied by certain challenges, and often already the collection of these data is a vastly expensive process, especially when collecting longitudinal data with repeated assessments of multiple data modalities over time. Furthermore, such longitudinal studies often experience irregularities in the assessment frequency, for example, participants that miss certain assessments during the study or drop out before the study termination. Both of these instances introduce missing data into the collected dataset, which makes its subsequent analysis more difficult. Then again, patient-level data are human data, and therefore they are subject to high data privacy. Governments enforce strict regulations on the sharing of this data, for example, the GDPR in the European Union, which on the one hand side ensure the data protection, but on the other also severely complicate the data sharing process across research organizations. And as all real-world data, also clinical study participants are sampled from statistical distributions of some sort. And we can use AI and machine learning methods from the field of generative models to leverage upon this fact and learn the data underlying statistical distribution. By training a generative model on real-world data instances, the model can learn the data underlying distribution, and subsequently we can use this learned distribution to draw further samples from it. These newly drawn samples are what is often called synthetic data. And in our case, this would correspond to synthetic patients that are not connected to any real human being, but still follow the characteristics of the real data. As such, a synthetic dataset containing these artificial data points would also exhibit the same signals that can be found in the real data. So, for example, progression trends of biological markers. Biomedical research can benefit from such synthetic datasets in various forms. So we could, for example, enrich real-world patient datasets with synthetic data to achieve a higher temporal resolution by interpolating intermediate assessments in between real observations, or by extrapolating more assessment follow-ups after the study termination. We can also simply increase the sample size of our study population by mixing in some synthetic patients into the real dataset. However, also completely synthetic datasets have their use cases in the biomedical domain. For example, the FDA and EMA have already discussed the approval of synthetic control arms in clinical studies. So using synthetic control arms would increase the speed of clinical trial because we don't have to recruit participants anymore. And then again, it also makes the whole process way cheaper. Also, data sharing of synthetic data should be more easy than sharing the real data itself, because the synthetic data is not connected to any real human being, and as such is also no concern of data privacy. One method to generate such synthetic data are the neural ordinary differential equations that are also called neural ODEs in short. They have been introduced by Chen et al. In 2018 in a NeurIPS conference. It's basically a machine learning hybrid approach which fuses artificial neural networks and ordinary differential equations. And the idea here is that we parameterize the gradient of an ODE system using a neural network. And in contrast to more ordinary neural networks that work over a discrete amount of layers, this aspect allows us to evaluate the hidden state of a network in infinitely small time intervals because we work with the gradient here. And thus, we enable the modeling and also subsequent generation of variable dynamics on a continuous time scale. However, neural ODEs still come with some limitations that hamper their applicability to clinical data. For once, they only work on time series data, and as such, static variables cannot be taken into account to model variables. And then again, they can't deal with missing data. So both of these limitations are pretty severe when we talk about clinical data, because we have a lot of missing data most often. And also we are interested in the effect that, for example, biological sex or genetic markers, which are also static, have onto the trajectories of certain biomarkers. To overcome these limitations and make the concept of neural ODEs applicable to patient-level clinical data, we designed the multimodal neural ODE, also called multinode. In the following slides, I will briefly introduce the model architecture, starting with the neural ODE module shown here in the orange box. So here, the longitudinal variables of the input data are pushed through a recurrent encoder that generates a latent embedding of the longitudinal variables, which then forms the initial condition for the ODE solver. The output of the ODE solver is then decoded back into data space and gives the longitudinal variables again in data space. To include the static information here, we again append another variational autoencoder structure to the multinode structure here, which was originally introduced by Nazarbal et al. In 2020. It's also called a HIVI. And here we take the static variables, we encode them into a latent space, and then we receive a latent distribution of the static variables, which we now concatenate onto the latent representation of the longitudinal variables. And now, by using this augmented initial condition here as a starting point for the ODE solver, we make the longitudinal trajectories that are learned in the ODE also dependent on the static variables themselves. To deal with missing data, we also introduce an imputation layer here, which is a concept that our group has already published previously. And this is a way of implicitly imputing missing values during model training. So by combining all of these aspects, our multinodes are capable of dealing with multimodal heterogeneous data and also with missing values. And now we can also generate synthetic data from these models by sampling a random latent distribution in the latent space here, both for the static and the longitudinal variables. We augment them to build the initial condition for the ODE solver, and then decode the resulting output back into data space. And this decoded output then represents the artificial longitudinal data. And to get the artificial static data, we decode the randomly sampled static latent representation directly through the HIVI module that we see here on top and gain the corresponding data in data space. So now we tested this framework also on a clinical data set, namely the Parkinson's Progression Markers Initiative. And this is a Parkinson's disease data set which has 354 de novo Parkinson's disease patients. And we used 25 longitudinal variables that are reported in the data set. And this is, for example, tremor scores or clinical assessments, and also 43 static variables, which are, for example, the biological sex, but also genetic variations such as SNPs, for example. And we evaluated the multinode in several tasks. So the overall goal was to generate synthetic data that mimics the realistic data properties. And we compare this generative capability against a previously published approach that is also for generating synthetic clinical data called the variational autoencoder modular Bayesian network. Then again, we also assess the interpolation, extrapolation capabilities of the multinode. So here you can see the real marginal distributions in blue of certain variables at a certain time point. So the distributions encountered in the PPMI data. And then in red, we see the distributions in the synthetic data generated using multinode. And in green, we can see the distributions of the synthetic data generated using the Wamben approach. And in all of the cases, the generated marginal distributions came quite close to the real distributions for both of the approaches. And in 52% of the variables, the Kullback-Leibler divergence between the multinode synthetic data and the real data was smaller than compared to the Wamben and the real data. So the performance is similar on population level, but now we would also be interested in how realistic single data instances are. And therefore, it's really important that we look into the variable interdependencies, for example, represented through the correlation structure that we found in the data. So here we have 3 heat maps, each showing the Spearman rank correlation coefficients for each the real data and the synthetic data sets. And we can directly see on first sight that the correlations are better captured by multimode compared to the Wamben approach, which again means that if we synthesize single instances, they are more realistic coming from the multinodes because their variable interdependencies are more accurately captured. Wamben, furthermore, is a model that can only operate on a discrete timescale. However, with multinode, we can go beyond the discrete timescale into a time continuous setting. And this is what we show here. So here we generated in red shown a longitudinal trajectory of a certain variable of the PPMI data set and compared it to the real data here indicated by the blue bars. And you can see in these examples, and this actually holds true for all the longitudinal data variables in the data set, that the generated data and the real data were highly overlapping and really similar. So this even counts for highly non-linear structures, as for example here the KIP variable down in the left. Now, to evaluate how well our model is capable of extrapolating and interpolating data points, we have tested 2 scenarios. For the extrapolation, we trained the model only on the first 24 months, and then we try to extrapolate the remaining time points. So here you see an example of that, where we extrapolated the last 2 visits and then again compared how far the extrapolated data fits with the left out real data. And again, in the vast majority of the variables, we saw a really close fit, and in 88% of them, the 95% confidence intervals between the real data and the extrapolated data are overlapping. Also looking into the distributions of the extrapolated time points compared to the real time points, we can see, for example, that the mean and median are always really closely fit. For the interpolation setting, we took the time series and left out 1 intermediate visit during model training, and then generated data also for this intermediate visit. And here again in red, you can see the generated data. And in the box, we can see that, again, the red generated data here is hugely overlapping with the real data indicated by the blue bar. And this, again, holds true for 82% of the longitudinal variables that we looked at. And again, as has been the case for the extrapolated data, also for the interpolated data, the marginal distribution at the interpolated time points fairly closely resemble the real data marginal distributions, and especially the mean and median are tightly fit. So in conclusion, multinodes are a generative model that can handle heterogeneous and complex clinical data combining both longitudinal and static variables, and they can also be used to then generate realistic synthetic data sets. And this not only on a discrete time scale, but also on a time continuous scale, which allows for smooth interpolation and extrapolation. We could use these models, for example, to enrich real data sets, especially because of the interpolation and extrapolation capabilities, and to make assessment intervals in real world data more regular. But we could also generate synthetic data sets with any arbitrary follow-up intervals or follow-up times. And they are always without missing data. Then again, we see that multinodes are also really good in generating realistic single data instances because they quite accurately capture the correlations that we also see in the real data, and therefore the variable interdependencies are captured. With that, I would like to thank you for your attention, and I'm happy to discuss any questions.